Welcome students. In this lecture, we shall understand what is a three-level laser and we shall discuss its rate equations by using a simple model. You know that a ruby laser is an example of a three-level laser. Three-level laser. In order to produce a steady state population inversion, 3 or 4 level laser system is used. Usually, we have seen during our last lecture that a 2 level laser system is not successful because because we cannot obtain a steady state population inversion by just pumping between two levels, and we need a third level at least for maintaining a metastable state. As you see in this diagram, we have a pump signal. H nu P is the energy incident, and there are two levels, three levels rather, E1, E2 and E3. E1 is the ground level, and the number density of atoms, active atoms here is N1. Then in the metastable level it is N2, and in the excited level, which is usually a continuum of levels, that means it is a broad level, we have N3, the number density. What pump does? Pump lifts the atoms from ground state to level 3, where they undergo a rapid decay to level 2, and then from level 2 we have a signal which is stimulating it and which causes the laser action. Let nu1 be the frequency of that signal, which lets them fall to to the ground level atoms. Atom which pumps the atom, which forces the atoms to jump to the ground level, and a radiation of a coherent radiation of frequency nu1 is emitted. Now, this process of rapid decay is of two types. It comprises of the radiative as well as non-radiative transitions. As we discussed, level 2 is the upper lasing level, 3 is not a lasing level, lower level is the ground level, and relaxation from 3 to 2 is very fast. A broadband light source is used as a pump source to lift the atoms up. To derive the rate equation and to justify the limiting conditions of power, what is the threshold, we consider again the energy level diagram. The total number of atoms, active atoms, remains conserved. That means the atoms at level 1, 2 and 3, the total sum is n. N is the total number of atoms per unit volume. That means the number density of atoms. Now we can very easily understand the rate equation by considering here the you know that the rate of upward transition depends on the probability of transition and the number of active species present over there, that means at that level. So here this journey, upward journey, I can write plus WPN1 stimulated absorption. Similarly, the downward journey I can write minus WPN3 because this is level N3. So the rate is proportional to the number of active species present here. Now this is stimulated transition, and as I told you, there is a spontaneous transition also from 3 to 2, which is responsible for the for maintaining a population inversion. So here it is the it is T. T is the rate of transition, as you will see next also, from 3 to 2, and because it is decaying here, so minus 3 T3 to N proportional to proportional to the number of atoms present there. This we have seen from the Einstein equations. In Einstein equations, Einstein modeled the stimulated and spontaneous transitions and gave his theory of radiation that we had discussed in our earlier lecture. So again, under the action of a pump source, we see an upward absorption, that means upward journey, that means stimulated absorption under the stimulating radiation is possible with the probability W1 and the number of atoms present N1. Similarly, a downward, because stimulated is two-way and spontaneous is a single way process, one-way process. Stimulated is two-way and spontaneous is one-way process. So here T21 decays at level N2, which is again spontaneous. Here it is spontaneous. So to summarize it, we can see very easily, we can separate stimulated and spontaneous transitions. You see, first of all, it pumps up the atoms, then it depletes level 1. So when it is being pumped up, it is being depleted. And when it makes downward transition, it is being populated, level 1, because W1 is similarly the ground level is being populated from level 2 and it is being depleted also. But when it is being populated, we have N2, and when it is being depleted, we have N1. Similar is the story with when it is being populated, we have N3. When it is being depleted, we have N1. Now next, the level 1 is being populated by atoms from level 2 by a speedy radiative transition. Now the story for level 2, when it is being populated by a lasing radiation, it is proportional to 1 and N1, and while it is being depleted, it goes to the lower level, ground level is proportional to N2. Then it is being populated by level 3, but it is being depleted by level transition from 2 to 1, but the rate is proportional to N2. Similarly, for N3, it is being depleted to level 1 and it is being populated by atoms from 1. Then we have the speedy transitions from 3 to 2, which depletes it. Now we can summarize it in one more way to give a better understanding. We see stimulated and spontaneous transitions. The train from station 1 to 3 and from 3 to 1. Level 1 is being depleted. Here level, because of this action, 3 is being populated. During journey from 3 to 1, level 1 is being populated. You see, and 3. Level 3 is being depleted. You see, N3. And equation. Here also same equation. As far as the story of journey from 1 to 2 and 2 to 1 is concerned, we see under the action of leasing radiation, we have level 1 is being depleted during upward transition, and the same, because of it is conserved, level 2 is being populated, and vice versa. As far as spontaneous transition is concerned, the journey is one way, 3 to 1 and 2 to 3 to 2 and 2 to 1. During 2 to 1, this must be here and this must be here. Well, it doesn't matter much, because here we can change it. I can write 2 to 1 and this one 3 to 1, and you see it is proportional to level 2, 2 to 1, and it is here conserved. Similarly, during 3 to 2, we have it is being populated, and by the same process it is being depleted. 3 is being depleted. So we can very easily write the rate equations using this knowledge. You see, W dn1 by dt is equals to Wp n3 minus n1 plus W1 n2 minus n1 minus T3 plus n2 T21 n2 T21. Similarly, n2 is equals to W1 n1 minus W2 n2 minus T21 n2 T32 n3. And last but not the least, this one WPN1 minus WPN3 and T32N3. WP is the rate of pumping from 1 to 3 and T32 is the rate of transitions, radiative as well as non-radiative. As we discussed during two-level laser, non-radiative is due to the vibration, rotation and so on that increases the thermal energy of and is not transmitted in useful radiation and it increases the heat. So if we select the active material such a way that this is negligible, then the output efficiency will be more. So approximately I can say T is nearly equal to A, that means radiative transition in most of the lasers. As we discussed during our initial lectures uh, of the basic theory, we saw that the probability is equal to pi square of pump signal or the lasing action, lasing signal, pi square by h cross omega c by omega n naught A21, which is the inverse of the spontaneous relaxation rate. Then there is a line width and line shape function and the intensity. Now, as the steady state is reached, because the numbers are conserved, we see that dn1 by dt is 0, dn2 by dt is 0 and dn3 by dt is 0. So we can put all these equal to 0. And we have got three equations. Using these equations, we can simplify them. You see, it is very easy to simplify putting this equal to 0. I have Wp n1 minus Wp plus T32 into n1 n3 equal to 0. So I obtain in terms of n1 the value of n3, number density of n3 equal to Wp by Wp plus T32. It is less than n1. Substituting this from this value in the equations 3b and 3c, we can eliminate n3 and we obtain an equation between N2 and N1, N2 and N1, which is very useful equation. Now I have N3 equal to Wp by Wp plus T3 to N1, and N2 we have seen is this equation 4b, and substituting back substitution in the original equation, what I get, N equal to Wp plus T3 to W1 plus T21. You have just taken the LCM, and from 4b we obtain N2 minus N1 by just subtracting N1 on either side. Here we must write N1 also. Now using dividing 5a by 5b, dividing equation 5b by 5a rather, we eliminate N1 on RHS, and what we obtain, a very deciding equation for population inversion and for a sustained laser oscillations. We must have the this must be a positive quantity. For this we have Wp T32 minus T21, this must be positive, definite, minus T32 into T21 must be positive. Otherwise, when population inversion is not there, N1 must be greater than N2. So simplifying it, we get T32 is greater than T2. That means the transition from 3 to 2, the rate of transition, the probability of transition from 3 to 2 must be greater than that from 2 to 1. That is the necessary condition. A relaxation rate of 3 must be greater than that of 2. Lifetime of, therefore, the lifetime of level 3 must be smaller than that of 2. To obtain the minimum threshold pump rate, we again use this equation. This must be greater than or at least equal to 0, at the most equal to 0. That means greater than or equal to 0. So from here we see that the threshold pump rate must be equal to T32 into T21 by T32 minus T21. Now if both are equal, then the probability becomes infinite. Why? Because the threshold pump rate needed is becomes infinite. So I have T32 much greater than T21 and T32 minus T21 is nearly equal to T2 because I can neglect it in the denominator. So the threshold pump power is equal to T21. Now substituting it back, we obtain this equation by a simple mathematical calculation, manipulation, and neglecting these things here. I obtain T32 bracket WP minus T21, and similarly is the case in denominator. And by pulling it out, WP plus T21, I write it in a very simplified form. Below threshold, the pump rate W1 is very small, and we obtain by neglecting this thing here, because W1 is very small. N2 minus N1 by N is nearly equal to WP minus T21 by WP plus T21. This is the threshold, this is the pump rate for stimulating atoms, and this is the T21 is the rate of spontaneous transitions, that means during the laser action. Exponential amplification of beam. When stimulated transition rate per atom, it is, as we have already seen, is very small, negligible. The population inversion is independent of I1, and we see that di by dz for gain, it must be like this. I must be equal to I naught. Its solution is this thing, I naught e raised to plus alpha z. There is an exponential amplification of the beam. Once the laser starts oscillating, W1 becomes large. And when W1 becomes large, it disturbs the approximation here. From equation 10, we see that N2 minus N1 is reduced, and it reduces the amplification when the laser oscillates under a steady state condition. The intensity of radiation at the laser transition increases to the threshold value. Show that in a 3-level laser below threshold steady state condition, the number density of atoms being lifted per unit time from 1 to 2 via level 3 must be equal to the spontaneous transition rate per unit volume. Now, spontaneous transition rates we have seen, and it can be very easily proved. If T32 is very large, that means the transition is very fast from 3 to 2. The population of 3 must be very small, so we can neglect N3. So I can write N2 minus N equal to N2 plus N. On the RHS half, I have WP minus T21 by WP plus T21. By applying simple component dou and definite dou and algebraic manipulation, simple, elementary, we obtain WP N1 equal to T21 into N2. That means the rate of number density of atoms being pumped from 1 to 2 via level 3 must be equal to the spontaneous emission rate. So this is the pump rate actually, and it is stimulated from between 1 and 3, and this chap is from 2 to 1. That means lasing spontaneous transition. So we have related the stimulated and spontaneous rates by using this simple theory. Absorption coefficient. Absorption coefficient we have seen in the earlier chapters that alpha equal to alpha naught. It is first of all equal to minus pi square c by omega n naught square 1 by spontaneous transition rate line width n into I have just substituted delta n, value of delta n, and if I put all these equal to alpha naught, because it is going to be constant for one particular situation set of parameters, I obtain the absorption coefficient equal to alpha naught by this thing in the denominator. Small signal gain coefficient, then we have on substituting we have alpha equal to alpha naught 1 plus I1 by Is. Here rest of this thing is Is, and G tilde omega. W1 is equal to I1, and I saturation is the inverse of this thing, and G omega is equal to G omega naught G tilde omega. As we have already seen that G tilde omega is like this. G omega naught is here usually equal to 1. So this is the line with shape function. It is all for now, and we shall in the next lecture we shall have we can study we will study rather the 4-level laser system and few more things. So till then, go through this theory from it is one of the good books, Professor Tyagarajan and Ghatak, and rest of the books are Oswald, Oswaldo, Yariv, one is this thing, another is this thing, then Demtroder is there. So many more number of books you may find, and just make notes. So bye for now, and till then we will meet again. Thank you very much.